Now need to find the field on the axis of a ring charge. What is a ring charge? The charged object is in the form of a ring, and if you take the axis of this, where is the axis? Now this is the axis where I'm holding my pointer. This is the ring charge and this is its axis. Can you see that? We need to find the electric field at a point on the axis of a charged ring. Alright, consider a ring of radius A. Here is a ring of radius A that carries an amount of charge Q, and its center is at the origin. Now the center is the origin, the radius of the ring is A, and this is the axis of the ring. You see, my axis is tilted because I placed the ring a little tilted. But remember, this axis is at right angles to the plane of the ring. Alright, we take a point P on the axis of the ring. We need to find the electric field at that point. Now you need to listen carefully. I'm going to go a little fast with this. Now point P is at a distance x from the origin. The origin is at the center of the ring. What we do is we start by taking a small charge, a small segment dq. The point P is on the x-axis at a distance x from the origin. In order to find the field at P due to the charge on the entire ring, we take a small element of the ring which has a charge dq. You see? We take a small element of the ring that carries a small charge dq, and we find the electric field at P due to that dq. Now, the charge dq is at a distance r from P. Can you calculate that distance r? This distance r is the hypotenuse of this right triangle, where this distance is x and this distance is a. Therefore, this r squared equal to a squared plus x squared. So the square of the distance from dq to P is r squared equal to a squared plus x squared. Therefore, the field dE at P due to this charge dq will be, what's the equation? Will be k dq over r squared. That's right. K dq over r squared, and that will be k dq over r squared is a squared plus x squared. Now tell me, what is the direction of this electric field? This is a positive charge. The ring carries a positive charge. That means the electric field will be directed away from it. That will be the direction of the electric field, and that is dE. Well, this field dE makes an angle theta with the x-axis. You see that? Now, we need to break this into x and y components in order to study that. So we need that angle. So let's say dE makes an angle theta with the x-axis. Okay? dE has a component dE cos theta along the x-axis and dE sine theta at right angles to the x-axis. Is that right? Now you know how to break a vector into its x and y components. So this dE has a component dE cos theta, well, dE cos theta in the x direction, and dE sine theta, it is the y component. Now, an element dq on the opposite end, if you now take an element dq exactly opposite to there, you will get a similar dE, that as the same components dE cos theta and dE sin theta. Can you understand that? If you take a similar element of charge dq, it will produce an electric field the same amount but directed that way at an angle theta with the positive x-axis. If this is a negative angle, that will be a positive angle. And this dE will have a dEx, the x component, dE cos theta, and a y component, dE sin theta. And if you now notice the symmetry of the ring, one very interesting thing happens. All the components at right angles to the x-axis. You see, you can now construct many such dEs by taking elements all over the ring. For every element on one side of the ring, there is a similar element on the other side. That means you can construct these all around the points which will have x components all directed in the x direction and the y components each opposing each other. What that means is all these y components will cancel and all the x components will add up. So all the components at right angles to the x-axis. You see, for dq on either side here, these two will cancel. If you take another pairs of dq anywhere, again those components will cancel and the x components will add up. Only dEx will survive the components along the x-axis. So we need only look at the x component, all the y components will cancel. And that dE equal to k dq over a squared plus x squared, and its x component will be therefore dE cos theta. So the x component is dE cos theta, where dE is this quantity, and we now work with this. Now, what all now we need to do is we need to find that the value of the cos theta. Can you find the value of cos theta? If this angle is theta, then the angle opposite to that is this is also theta. What is cos theta? Cos theta is adjacent side divided by hypotenuse. Adjacent side is x. Hypotenuse is square root of r squared, which is square root of a squared plus x squared. So I can now write, I'm going to write cos theta as x over square root of a squared plus x squared. I hope you understand that. R squared is a squared plus x squared. Therefore, r equal to square root of a squared plus x squared. And cos theta is x over r, which is x over square root of a squared plus x squared. Alright? Now that will be, let's combine this together. That will be kx times, or kx divided by a squared plus x squared to the power of 3 over 2 dq. I took that dq and put it there and combined all the remaining together. Kx divided by a squared plus x squared times square root a squared plus x squared. I'm sure you know that is written as a squared plus x squared to the power of 3 over 2. And this is the x component of the electric field due to one small element of charge dq. And in order to find the total field at P, what all we need to do is integrate that from Q equal to 0 to the total Q. The total field Ex at P is integral of this quantity. And if you notice, kx over a squared plus x squared to the power of 3 over 2 is a constant, because x is the distance of the point from the center of the ring. That doesn't change. And a is the radius of the ring. That doesn't change. So none of these will change. And so we can take that out, and that now become kx over a squared plus x squared to the power of 3 over 2 integral dq. What is integral dq? Integral dq is the total charge q on the ring. So that gets us the final equation for the electric field at this point as kqx over a squared plus x squared to the power of 3 over 2. So you must remember that equation. The electric field at a point on the axis of a ring charge is kqx. Q is the total charge on the ring. X is the distance of the point from the center of the ring. And A is the radius of the ring. kqx over a squared plus x squared to the power of 3 over 2. When x is very large compared to a, what can we do? When x is very large compared to a, you can take a squared plus x squared is approximately equal to x squared. And x squared to the power of 3 over 2 will be x cubed. And x divided by x cubed will leave an x squared on the denominator. It will come to ex equal to kqx over x cubed, because this quantity will become x cubed. And that will be kq divided by x squared, the same old formula that we derived earlier. In other words, when you take a point that is very far from the ring, the charge carried by the ring can be considered to be a point charge. That is what it means. Let's do an example. 2.75 microcoulomb is uniformly distributed on a ring of radius 8.5 centimeter. Q equal to 2.75 microcoulomb. Find the electric field on the axis at 1.2 centimeter from the center, 3.6 centimeter from the center, 4 meter from the center of the ring. Well, we know the radius is given, which is 8.5 centimeter, 0.085 meter. The charge carried by the ring is 2.75 microcoulomb. And in A, x equal to 0.012 meter. Well, we will use the exact formula for that. E equal to kqx over a squared plus x squared to the power of 3 over 2. Alright? Just replace all the values. kq in coulombs times x, a squared plus x squared to the power of 3 over 2, and use this on your calculator and see whether you get that value. 4.7 times 10 to the 5 Newton per coulomb. Alright, and for B part, the only difference is x will now become 3.6 centimeter or 0.03